How the universe works.
We start at the beginning of our known universe with a bang. Our universe began with a massive singularity. In less than a second, all known matter came into existence. This universal expansion was discovered by analyses of redshift in planets and other celestial bodies throughout space. Edwin Hubble concluded that all galaxies seemed to be moving away from each other. Billions of particles were released across space, some collected into the building blocks of matter.
A star starts its life cycle as a nebula. Nebula is made out of gas and dust, and over time, the cloud contracts and begins to form a disk shape. This is a protostar. What makes a star begin its actual life is the process of converting raw elements into energy, a process known as fusion. The star's life cycle.
Hydrogen is the element that is being converted as the star collapses in on itself. This burst of energy is balanced by the opposing force of gravity, and the star is held in an energy equilibrium, known as the main sequence phase. Stars can stay in a state of fusion for millions of years, long enough to emit a stable amount of radiation, which will later be essential to creating life on other planets. When the star's fusion ends, depending on the predetermined mass of the star, it could take the path of either a red giant or a super red giant.
A more massive star will lead to a more massive death later on. Fusion is halted at this stage, and the star will either collapse and explode into a supernova if it is more massive, or a spinning tiny object known as a neutron star that gives off X radiation. If the star dies here, it could revert into an incredibly dense object in space, so dense gravity bends time and space around it, known as a black hole.
This is the end of the life of a very massive star, but a smaller star's life does not go out with a bang, but a fizzle. The less massive star will slowly lose its cloud of elements and release them into space, which will later form a planetary nebula. After the cloud of elements is shed, the remaining mass is a semi-bright object with little energy left, known as a white dwarf. As the white dwarf loses its luminosity, it becomes a black dwarf, not to be confused with a black hole. This object is much less dense. Here ends the life of a star.
The formation of our solar system. The difference between a planet and a star is the absence of fusion. To create a planet, we will start at a planetary nebula, which has formed after the death of a star. Matter in the planetary nebula starts to attract to each other using static electricity, a process known as accretion. Over time, these particles form into larger and larger particles until they have enough mass to have their own gravitational pull. This pull acts on each other until these small particles form larger asteroids.
Gravity clumps the asteroids and particulates together, and leftover elements from the formation of the star, which our planet will later revolve around, sink into the planet. In the particular case of our Earth, denser elements sink to the core, because gravity was evenly distributed as a force on the new round object. The elements are dense and radioactive. They will form the core of our Earth. The whole planet is hot and unsettled when another celestial body collides with our early Earth, scattering dust and asteroids into space around the planet. The particulates that were scattered begin to clump into smaller bodies, which fall into orbit around the Earth. As it becomes more and more massive, these bodies will combine to form our moon. By gathering evidence from relative timestamps left on Earth, such as meteorites and other objects from space that hurtled into our planet when it was being formed, we can use a process called relative and radiometric dating to track the origins of our planet.